Okay, I'm going to, in this little video, go through the answers to questions 1 to 10 for you, and you're going to use this to annotate your paper, annotate your script, write in how to do the right answers, and as a result, I'm going to take that and check that you've done that well, and then you're going to have something that's going to help you to revise for the exams in January. Alright, let's get started. Question number 1. Objects accelerated by a constant force F. We know that F equals ma, no surprises there, and therefore the force is proportional to the acceleration. If you've got a force acting on something, it's accelerating, i.e. the velocity is increasing. So you think about what constant acceleration looks like on a velocity time graph, a VT graph. What you have is a straight line like that. Now, therefore, if the velocity time graph's going up with a straight line, then you think about velocity times by mass, the momentum is going to go up with a straight line. So straight away we could say it's got to be either A or C. It can't be these two, okay, because they're just not fitting the bill. Now, once we've done this, let's think about the kinetic energy. Well, we know the kinetic energy, Ke, is equal to a half mv squared. Now, that basically means it's proportional to v squared. Given the mass, it's going to stay the same. So if we think if the velocity is increasing with a uniform increase, the kinetic energy is going to go up with a parabolic x squared function increase. So that's got to be A. Ka-ching. Alright, let's have a think about this. Power, efficiency. Well, we know efficiency is equal to the total useful out divided by the total in. And you can multiply it by 100 to make it to percent at the end, but let's just leave that as that for now. Okay, so the useful energy we're getting out of this, or the useful power we're getting out of it, is the number of joules per second. Well, it's going to be mgh is just the it's basically just the gravitational potential energy, but we want to know the power which is being developed, which is going to be the height per second, h per s, h over s, I'm going to say. Okay, now on the bottom basically it's the useful total energy, which is just going to be joules per second. You can see we've got per second on both sides, so you can almost forget about them. We can forget about them. So thinking about this, or looking at this now, what's the mass? Well, it's 10. What's gravity? Looking at this, I know it's 9.81, but it's near enough 10, times by the height per second, which is 0.5 meters per second, divided by the energy in, or 100 joules per second. Of course I've got per second there, so I'm forgetting about it. Okie dokie. 10 times by 10 is 100, times by half is 50, 50 divided by 100, times by 100, if you want to put times 100 on the end, it's still just 50. So, there you go, 50%. Alright, that's the first thing. Obviously, you know, we consider that to be 10 in this case. Alright, question number 3. Now these ones are beasts. There's no two ways about it. There's nothing nice about this. But this is why, if you do get yourself an A at physics, you can be sure that you're a very clever person, because these things are here to test you. So, how much momentum is carried by the water leaving the hose per second? Well, we've got to put two things together for this. First of all, we know momentum P is mass times by velocity. So, what is the mass that's leaving per second? We've got a volume per second and a density. So I'm going to say the mass is density times by volume, which is of course 1,000 times by, in this case, 2 times 10 to the minus 4. 2 times 10 to the minus 4. That's going to be our mass that's leaving each second. So that's cool. That's going to, this lot here will go in for mass. Velocity though is a bit trickier. Well, in order to work out, because it doesn't say the velocity, we just know that it's going out at a volume rate. So we know what's the relation between the velocity and the volume per second. Well, the answer is this. Volume, and I'm going to put volume per second, s to the minus 1, is going to be equal to area times by length. Now if that's volume per second, this is volume, that's volume, this is volume per second, this is length per second. I just put in a slash s and messing around. I should put s to the minus 1. But the point is, I got s to minus 1 on both sides. So I know the volume is 2 times 10 to the minus 4, and the area is that. So if I divide volume by the area, I'm going to get the length per second. If I get volume per second divided by the area, I'm going to get the length per second, which is, of course, you've probably worked out already, velocity. Okay, so that'll be 2 times 10 to the minus 4 divided by the area, which is 7.2 times 10 to the minus 4. That's going to give me the velocity. Alright, so I'm going to take this lot. That's going to be the velocity term. This lot, that's going to be the mass term. Okay, so getting the calculator, shoving that in. Let's do the mass bit first. 1000 times by 2 times 10 to the minus 4 equals, that's the mass, times by the volume, velocity, which is going to be 2 times 10 to the minus 4 divided by 7.2 times 10 to the minus 4 gives me 0.5555, which is 5.6 times 10 to the minus 2 kilograms meters per second, or Newton seconds, because if you look at it, if we just remember Ft equals delta mv. Okay, so this is an alternative to unit for momentum. Okie dokie, question number 4. Now, this one's tricky, really. You know it's not conservation, mate, that's just pants. You know it's not conservation, that's just pants. It's Newton's first law, Newton's third law. And I can easily understand why people could get this wrong. And I think you could almost argue it could be anything, until you look and notice what this little symbol here says, and that's a W. Now, what does W always stand for? It is weight. Okay, so what we have here is a weight force acting down, and then N, which is the normal reaction force acting back. Now, if this is, this could be anything you want, but the fact we know this is the weight, gives it away that this is a reaction to the weight. Therefore, if body A, there we go, exerts a force, the weight, on body B, there you go, the floor, then body B exerts an equal and opposite force on body A. Hence, it's Newton's third law. And I know I can understand why you could say, well, it's at rest, so it's Newton's first, but it's the fact that that's a W that gives it away to you. Alright, let's look on. Number 5, a car exerts a driving force of 500 at constant speed of jibbity flip. What work is done in 5 minutes? Well, we want to know how far it goes in 5 minutes, really. Work done is force times distance. WD is F times distance, force times displacement S. So this is 72 kilometers per hour. Now I'm going to let you into a secret. 72 kilometers, that's thousands. So 72,000 divided by the number of seconds in an hour, which is 3600. That'll give you 20. Okay, so that's going to get 20 ms to the minus 1. You might want to write that in. 72,000 divided by 3600 equals 20. Okay, so that's that. Anyway, once you got that, we're going to get 20 meters per second, and we're doing it for 5 minutes. So it's going to be 20 times by how many seconds there are in 5 minutes? Well, it's 5 times 60, which is of course 300. 300 times 20 is 6,000. Is it? No, yeah, 6,000. 6 kilometers times by the force, which is 500. So that gives us, what does it give us? I'm going to work this out. 20 times by 5 times by 60 equals times 500 equals 3,000 or 3 million. There you go, it's A. Alright, so that's that. That's question 5. Nearly there. Which of the following is not a unit of power? Well, let's just think about what is power. Power equals energy divided by time, energy per unit time. So we know that for this first one, newtons times by meters, force times by distance, that's work done, s to the minus 1, well there you go, that's joules per second. Ching! This one, joules per second, that's basically dead straightforward, that is power. Now let's just look at these two. Well, which one of these is is going to be power, which one is not going to be power. Let's think this through. We know that the what's the base units of energy, basically. We need to think this through. Let's define first of all the Newton. F equals MA. Okay, so that's kilograms times by meters times by seconds to the -2. That is the Newton. Okay, and then if it's force times by distance, dunk, yeah, that is joules. Okay, so you can say, right, let's times this now by distance, s to the -2 times by distance becomes s to the -1, so that will become s to the -1, and then it's joules per second, oh sorry, meter, I'm talking rubbish, times by distance becomes meters squared, there we go, and that gives, this will now be the basis of the joule, kilograms meters squared, s to the -2 is joules, and we want joules per second, so we're going to divide it by time. It's going to be s to the -3. That is the unit. This is power. Okay, that's joules per second. That is the basis for power. That one is power. So the one it's not is D. Okay, there we go. D. Moving swiftly on. Total mass of 500 kg. Gravity is 10. What is the weight? Well, the W equals mg. That's going to be 500 times by 10. That's 5,000. Easy peasy. Now, what we've got to do is we want to say, well, what's the tension of the cable? We know that if it's hanging dead still, it's going to be 5,000. But it's not hanging dead still. It's pulling itself up. So it's going to be more than that, isn't it? Basically, if you had a cable, the occupants are stationary and it's exerting 5,000 newtons, then you start accelerating up, it's going to be more. And there's only one value on here that's more than 5,000, so it's got to be that one, basically. And away we go. Alrighty, number 8. Firework fired into the air and explodes at its highest point. Okay, we're not entirely sure if it's gone up, it's just stopped, it's going to come back down, or whether it's going off at an angle like that. But the point is, it's probably going at its slowest point at that precise moment in time. Okay, so the slowest point of its journey is there at the top, and suddenly explodes. If it explodes, all the fragments are going to be going at different places, zooming off. And remember, kinetic energy is a scalar, it doesn't matter in what direction it's in, so it's going to be increased. So it's got to be one of these two, just in terms of the kinetic energy. Then you think about it, let's imagine that our rocket is stationary, doesn't matter, and it breaks into, in this case, 4 different fragments going in 4 different directions. If we made this the positive direction, then this is a negative direction, they're going to cancel each other out. If we make that positive direction, that's a negative direction, they're going to cancel each other out. The point is, all the fragments they won't have any more kinetic energy, momentum, sorry, as a result of the explosion. So they're going to remain the same, which is going to give us C. Right. A body falls through with negligible air resistance. What quantity of the body is its rate of change in momentum? Well, is it true to say that F equals delta mv over t? So the rate of change in momentum per unit time, the rate of change in momentum is equal to a force. So all we're looking for is something here that's a force. Is mass a force? No, it's not. Is power a force? No, it's not. Is kinetic energy a force? No, it's not. Is weight a force? Oh, yes, it is. There we go. Job's a good one. And then finally, question 10. Which of the following is a scalar quantity? This is simply a question of recall, okay? Velocity is a vector, it's got direction. Kinetic energy is a scalar, it doesn't have direction. Force is a vector, momentum is a vector, okay? So kinetic energy is the only one that's a scalar. Alright, that's the first 10 questions. I'm going to make a new video for this one.